Hello guys! Today we will speak about vectorization in pandas. We will also speak about numpy because, as you hopefully know, many pandas features are actually implemented in numpy. At the end of this video you will understand what the vectorization is and how it works, understand the benefits from vectorization, and see multiple examples of how the code can be sped up using vectorization. So, what is vectorization? Let's review one example that demonstrates us the idea. Generally, the vectorized operation, is the operation that is applied to the whole array instead of individual elements. Okay, let's first import pandas and numpy. Now we will create a list of numbers from 0 to 1 million and create a corresponding numpy array. Now let's use an explicit Python loop in order to calculate the sum of all elements in the list. In this case, we can say that the operation is applied to each particular element of the list rather than to the array as a whole. In this case, in the code below, we see that the operation is applied to the whole array, but we are not sure if it's vectorized or not. But at least we don't see any explicit Python loop here. And in the third case, we call a sum operation of the numpy array, and it produces the same result, and it doesn't have any explicit Python loop also. But if we look at the execution time of each operation, we see that explicit loop takes the longest amount of time. Sum, like Python sum, is about 6 times faster, but numpy implementation is even faster. So, in the first case, we have non-vectorized code. In the second case, we have optimized but not vectorized code. And the third case is vectorized. So you see that vectorized option is the fastest one. Generally, the benefits from vectorization are the following. First of all, if operation can be vectorized, it almost always works faster. Execution time is either constant in case of vectorized operation, or it grows much slower than the number of elements. We'll see multiple examples of such vectorized code a bit later. And vectorized code is often, but not always, is easier to read by a human. In the example above, you see that Python loop takes multiple lines of code, and a vectorized code is pretty simple to read. Okay, let's speak about the mechanism behind the vectorization. Why is it that fast? First of all, let's speak about the syst and simd. These are different approaches to data processing, and modern CPUs contain components both for syst and for simd data processing. Syst stands for single instruction, single data. Such a component processes one data element and one instruction per one moment of time, and it produces one result. Such components are pretty fast in terms of single elements processing, and they are very flexible. They can handle like many different operations. You can actually implement any algorithm on such a component. But if your data is very big and the data is of the same type, let's say a huge array of floats, and you want to apply the same operation, let's say sum up all these floats, syst is not the best option. In this case, single instruction multiple data component will be faster. So it also takes one operation, one instruction, but multiple data. So we have only like 3 elements drawn here, but in reality it can take thousands and tens of thousands of data elements at once. And it can produce multiple results per one moment of time. This component is usually limited to a specific amount of operations. But if the operation is supported by the simd component, then it can be sped up by many times. So you can see that in modern CPUs, for example, ARM CPU, there is some simd engine or simd component, and also the component that can make sys execution. And usually simd component is presented in each core of your CPU. So if you have like 8 cores, each core will contain a simd component. The code can be optimized not only by vectorization, but also by writing the algorithm in a lower level C in some optimized fashion. Here is an example of the numpy code that implements some algorithm in C. And you hopefully know that C language provides a huge amount of features and hacks that allow you to optimize your code. You even may notice that there is a goto operation here, which is a kind of not very good practice for modern developers, but sometimes it allows you to optimize the code. So vectorization is not the only option for speeding up your code. Just to sum up the things I've just said, the code that doesn't contain an explicit loop isn't necessarily vectorized. Here is an explicit Python loop, and you can also imagine this code to be written like this, like some operation applied to the whole array, or my array do some operation. These lines of code may be either vectorized or not. So there are actually 3 variants of what can happen. The first option is that the code behind this line is vectorized. It uses simd, and it's extremely fast. Like usually vectorized code is from 10 to 1,000 times faster than non-vectorized code. This code can be optimized using C loops, but not vectorized simd. This code will be also pretty fast, like normally it's from 1 to 10 times faster. And it may use a Python loop just under the hood. Like this loop may hide behind such a function. And this case will be not faster than just Python code. So just remember these 3 options. Let's review more specific examples of the vectorization. First of all, let's load a Kaggle train dataset. You may see that Kaggle train contains about 900 elements. And let's create a bigger dataset by repeating our small dataset 100 times. Now we have about 800,000 rows, which is pretty big amount. Okay, now let's calculate a modified value for a fair column in our data. So generally, this data contains rows for Titanic passengers, and they have like the name, sex, and also a fare that was paid by a specific person. And imagine that we want to transform the fare, like multiply it by some value and add some constant. For example, if we want to add, I don't know, taxes or something, some commission to the fare. In this case, code is executed for about 1 millisecond. And if you write the same code using a numpy vectorization, in this case we write like our data frame dot name of column dot values to access the underlying numpy array, and then multiply it by some number and add some number. So this code is executed much faster. You may notice that the execution time may differ from run to run, but generally the picture is pretty clear. And also, if you run the operation not on the numpy array, but on the entire column or the series, it's called pandas series, then the code is usually executed a bit slower because it should create a new series. And this operation takes more time. And this difference is noticeable on small data, but on bigger amounts of data it's not that noticeable because the overhead for series creation is not that big in comparison to the data processing time. And now if we repeat the same operation on our big data, we'll see that the execution time was increased by just small amount of time, even not twice. And if we do the same but create a new column, we will see that it takes almost the same amount of time. In many cases, the execution time will be a bit bigger than just series creation, but it doesn't differ dramatically. So you may see that the operation for a big data frame, which is 1,000 times bigger than a small data frame, is executed in about the same amount of milliseconds. And here is a list of operations that support vectorization in pandas and numpy. You may read pandas and numpy documentation to see more information about such methods that support vectorization, but it's a pretty long list. Okay, let's discuss more examples. The next one is the following. Imagine that you want to take the age column for your data and calculate the difference in the age between the consecutive passengers. To do this, you may use a shift function that shifts your data by, let's say, one row or other number of rows forward or backward. You may use also minus here to do the operation. Okay, the difference is calculated. And now we'll repeat the same for the big data frame. You see that it takes about 10 times more, while the data is 1,000 times bigger. And here is the demonstration of the result. We have these ages for the first 3 passengers. For the first passenger, the difference is not a number because we don't have a previous value or a previous passenger. For the second one, it's the difference between 38 and 22. And for the second, for the passenger with index number 2, it's 26 minus 38. This mechanism may be very useful for you if you calculate, for example, difference between prices in consecutive trades, or compare some transactions, or something that you want to see the difference between the consecutive elements. This operation can be vectorized and it works pretty fast. The next is splitting the data into bins. The best way to do this is to use pd.cut operation. It is pretty simple. You just provide your data series, in this case the age column, the boundaries of the bins, and the labels to assign to the resulting bins. And for the small data, it's executed during about 4 milliseconds. And here are the categories that we got. And now let's repeat the same for the big data. You see that it's about 7 times faster in this case, but normally it's by 5 or 10 times, sorry, not faster, but slower, while the data is 1,000 times bigger. The next use case is the calculation of value counts. Let's take our sex column and calculate the number of rows corresponding to each value of sex. So in small data, we have these values, and it's executed for 2.5 milliseconds. And for the big data, it's executed for about 50 times longer, which is also pretty cool. And using value counts, you can easily calculate the fractions of each value in your column by dividing the result by the length of your data frame. So you'll get the fraction. The next vectorized operation is .isIn, and we'll compare it to apply. Okay, let's run it. So we see that apply that checks the particular value to be in a list is executed for about 4 or 5 times longer than isIn. So isIn is much faster, and the result is the same as you see. Also, there is an option of like comparing. In our case, we just compare two values for two values, and we can write code in this way, but it will take even longer than our isIn call, like twice or 3 times longer. So isIn is pretty fast, and it's faster than apply. You should use isIn if you want to do this operation. The next one is mapping a value using some dictionary. In this case, we will map embarked column, which corresponds to the port of embarking. So here is it. So we have only one letter here, and imagine that we want to convert this letter to the full name of the place of embarking. Here is it. So if you use apply, you may notice that it takes more time, like twice more time than map. So in such a case, use map, it's much faster. Then one important notice about the group by. Group by itself is not vectorized, so let's run the code and see what happens. The operation, like max operation on the fair column, takes about 2 milliseconds. The group by for our data frame, let's say by age column, takes lots of time, like 100 milliseconds. And if we run like fair.max on our grouped object, it will take much more time than max on the fair column in the original data frame. Yes, intuitively we understand that there is much work here. We have to handle each category of our age and to produce the result, but remember that each category is smaller than the original data frame. And you may hope that all categories are processed in parallel, but in reality they are processed sequentially, and the operation on the grouped by object takes significantly more time than the operation on the original data frame. Of course, we remember that the results are different, but keep in mind that group by is pretty slow compared to like pure vectorized operation on the original data frame. One more interesting use case is that if you want to apply some filter to a column, you should apply it to the column, not to original data frame, and then access the column. So let's run the code and see the result. So in this case, we create man filter that produces true if the particular passenger is a man and false if it is a woman. So you may see that if we apply the filter to the data frame, then access the column and then calculate the max, it takes about 7 times more time than if we take the data frame and then the column, then apply the filter, and then calculate the max value. So this option is preferred and it's faster. Sometimes it's 4 times faster, sometimes it's even much faster. So guys, that's it for today. If you have any questions about vectorization or other topics in pandas, please write a comment to this video. Subscribe to my channel in order not to miss new videos about pandas, machine learning, and related stuff. Keep your self-education and take care. Bye-bye.